The Laplace transform is yet another very powerful tool to analyze LTIC systems. To understand why we need it, let's go back to the definition of the Fourier transform, x of omega, which is the Fourier transform of a signal x of t. It's given by the integral between minus infinity and infinity of the signal and time domain x of t times e to the minus j omega t dt. For some signals x of t, the integral can't be evaluated or doesn't exist for some frequencies omegas, or maybe even for no frequency omega. This means that the frequency response, or the Fourier transform of the signal x of t, doesn't exist. But if we would weigh the signal x of t with the exponential decaying signal e to the minus sigma t, so that the weighted version of x of t, which we could call x dash of t, is small enough such that the integral converges for all values of omega t, and hence we can indeed get a Fourier transform not of the original signal x of t, but instead of the signal x dash of t. All we would have to do is to choose sigma sufficiently large so that the exponential decay is sufficiently fast, and hence x dash of omega exists. And as long as x of t doesn't grow faster than exponential, we can always find such a sigma. But we can also express this slightly differently. Instead of combining the exponential decay e to the minus sigma t with the original signal, we can combine it with the other exponential function to get e to the minus sigma plus j omega times t. Then, if we define a new variable s, which is equal to sigma plus j omega, this is equal to the integral between minus infinity to infinity of our original signal x of t times e to the minus st dt. This is defined as a Laplace transform of the signal x of t, for which we often use the notation capital X of s. S is a complex variable with real part sigma and imaginary part omega. Since in signal processing we usually deal with causal signals in systems x of t, which are 0 for negative times t, the integral from minus infinity to 0 does not contribute to x of s, hence we can change the integral to go from 0 to infinity, which is called the unilateral Laplace transform. Despite this change, the same trick works. It means that we have to choose the real part of s, sigma, big enough to ensure that the Laplace transform x of s exists. So for some values of s, the Laplace transform x of s will exist, and for some values of s, x of s might not exist. The values of s for which x of s exists are collected in the region of convergence, which is often abbreviated as ROC. Consider, for example, the signal x of t, which is a causal exponential decay. The unilateral Laplace transform of x is called x of s, and it's given by the integral of e to the minus at times e to the minus st dt. This is equal to the integral of e to the minus s plus a times t dt, for which we can find the antiderivative. It's e to the minus a plus s times t divided by minus a plus s, which we will have to evaluate at 0 and infinity. This gives us minus 0 plus 1 divided by a plus s, which is equal to 1 divided by s plus a. Keep in mind that this only works for values of s which have a real part greater than minus a, which we can illustrate in the s-plane, which is a complex plane with the real part of s and the imaginary part of s. We know that x of s exists for all values of s which have real part greater than minus a. So x of s exists for all values of s to the right of this line here, for real part being equal to minus a. This region again is called the region of convergence, abbreviated as ROC.